Okay, so welcome back to another video. So today we have a little calculus problem, but this is dealing with a little bit of analysis. And suppose that we have some sequence of functions, we'll call this f sub n. The domain is in between n to n plus 1, the left interval being inclusive, and that maps to the range from 0 to 1 divided by 2 to the power n. With that, n can be the natural numbers, but also including the singleton set with element 0. I just put that notation down since depending on whatever textbook or professor you ask, 0 is part of the natural number set, or 0 is not part of the natural number set, but we're just going to make this little notation to include that element. And with also given that f sub n of x, the function, the sequence of functions itself is given with the following of the square root of x minus n, and then divided by 2 to the power n. And so today's question is, what is the sum of all of its areas if we're taking everything towards infinity? So here's a little visualization I drew of how the function looks. So suppose that if we were to plug 0 for sub f sub n of x, obviously you plug 0, so you'll get the square root of x, which is what the function looks like. So the max within that range in between from our domain would have to be that it goes all the way up to 1. Then if we put the next term in for n is equal to 1 is, so you'll notice that these ranges over here, they actually have a ratio, they decrease by halves. So you'll notice this goes by half, half, and half, like so on and so forth. So it's taken all the way up to infinity. So it's very, very, very like the minuscule area right there. So of course we want to know what is the area of all the entire shaded region altogether with like these discontinuities over here. The way to write this is very simple. It's just basically just write this as a infinite sum of the integrals between the domains for n to n plus 1, if we just define that. Then it's more of just taking the straightforward method and just evaluate each integrals at a time. Then we'll term-wise, then take the sum of all those evaluated, like iterated integrals, and then just get the finite value. So I will say one thing. So I'll write this down first. So I'll write this as a way of finding the area is equal to the infinite sum. So the infinite sum here, starting with n is equal to 0, of our integral from n to n plus 1 of the square root of x minus n, then divided by 2 to the power n dx. That's basically how the straightforward method is, but I was hoping that, so today's video is basically we're taking the long method. So we just go integrate each like piece or term wise and then just take the sum. So I was hoping for there might be a little detour on how to do that without having to go to that trouble. So if you'll notice that if we're just looking at the integrand itself, but it's also worth noting that this is actually the sum is actually converges absolutely, so we can actually interchange the sum. From there, you'll notice that, and I never talked about this function before, and this was new to me, it's new, you can actually write the infinite sum of this series as in a form of a Hurwitz zeta function. That's the relation with the Riemann zeta function and the Hurwitz function as well. That's kind of the tricky part on how to manipulate that from there. There is an integral representation of that, but that involves the gamma function, and the integrand itself is just all wacky all over the place. What I was hoping for that if using from that representation, this might convert into a double integral and then, go things from there. But sadly, like I can never like get past that step because again, it gets very wacky. So I'm hoping that, well, I attempted myself, but you can, if you want to, see if you can actually solve this, the infinite sum of this integral without having to do the expansion that I'm going to show in today's video. So if that's possible, leave a comment down below, and hopefully if you do like take the shortcuts using representations, then it will get to the final answer that you'll see at the end of this video. All right, enough rambling. I can't speak today. So let's actually just get started. Okay, so we're just going to focus on this iterated integral. So I'll write this as the integral from n to n plus 1. So we're just writing the same thing again. So x minus n, then divided by 2 to the power n dx. So we just take the just take the definite integral, just solve it and evaluate from there. So I'll just factor out a 1 divided by 2 to the power n. N does not depend on this integral. So now really we have n plus 1 and then n to the square root of x minus n dx, right? So obviously you'll notice that you can actually just perform a u substitution. So here we're going to let u equals we'll let u equals x minus n, and then du is just equal to dx. Okay, then if we just perform the necessary substitution, so it's 1 divided by 2 to the power n. I'm not going to calculate the new bounds. I'm just going to leave it the way it is. So here we just have so this will be u to the power 1/2 du. Set that equals, so now we would have so add the 1, so 3 over 2, then divide that, so we have 2 over 3. Then multiply with the 1 over 2 to the power n. Then we just substitute back for u, so there'll be x minus n, then divided by 3 to the power half, and then evaluate from n to n plus 1. This is very straightforward. Since you just plug n over here, then the whole term itself is just going to be 0, and if it's just n plus 1, so n plus 1 subtract n, the n is gone, so it's 1 to the power 3 over 2, which is just 1. So therefore we can just have that we find a little close form for whatever n we choose, or whatever n we're going to evaluate at each term wise. So we would have 2 to the power 3 then times 1 divided by 2 to the power n. So from there, this is just our little close form for any natural number n that we choose, but also including 0 as well, since I gave that notation. So I'll put this here. So now let's actually do things the long way. Okay, so here we take this area, so in other words, I'll have to do this 1 by 1. So if we just plug 0, so we just plug in term wise, so here we would have the integral from 0 to 1 of the square root of x dx. Then we add this with, now we go from 1 to 2, plug in 1, so it will be the square root of x minus 1, and then divide by 2 to the power 1. In this case, that's just 2. So I'll leave it at 2 to the power 1 just so the notation is easier to read in this situation. Then we keep going, so this will be 3 and then 2. So now this will be the square root of x subtract 2, and then divided by 2 to the power, so n, so in this case 2 to the power square. Then we just keep going on, so forth, so following up, and now we just go up to the n to the n plus 1, so that means n plus 1 and n square root of x minus n, then divided by 2 to the power n dn or dx. Now from here we can actually just do things one at a time and integrate these. So I can write this as 2 divided by 3. Then I just put in the closed form we have and just plug in 0. So I'll put it like this. So we have x and then subtract 0. So I'll put in this form right here. 0, 3 over 2, then 2 to the 0 power, go from 1 to 0, then add this 2 over 3. Same thing, x minus 1, 3 over 2, then divided by 2 to the power 1, go from 1 to 2. So you get the gist, that's how the pattern is designed. And then we just put in the closed form we have over here, plus 2 divided by 3 times 1 divided by 2 to the power n. Then, here, let me put it like this. I'll put the x minus n. So x minus n, then to the power 3 over 2, and then divided by 2 to the power n. Evaluate this from n plus 1 to, or n to n plus 1. Okay, so now we do this one at a time. So obviously you'll notice that for each of the n terms, so you'll notice that everything will just vanish. So really the only thing you have to evaluate is just the upper bounds for all the terms we just expanded out. Okay, so from here we will have 2 to the power 3. That's just from plugging 1 over here. So 1 is just 3, and then the 1 over here. So now add this with, let me group it like this. So we have 2 divided by 3, then add this with, or multiply, so plug in 2, so that'll just be 1. Like I said, everything from the lower bound that you plug, it's just going to vanish to 0, so you're only left to evaluate the upper bounds. So this will just be 2 over 3, then times 1/2, since we have 2 to the power 1. Then add this with 2 to the over 3, then multiply by 1 and then 2 square. Keep going on so forth. Then the last part, 2 over 3, then multiply with 1, then divided by 2 to the power n. So I'll put this little, I'll put in the little connotation, or rather symbols right here. So right here we have that this is just for 0. This is for 1. Like I'm talking about I'm talking about for n equals 0, n equals 1. Then over here it's just n is equal 2. So if I put it like that, let me just actually fix all this. Okay, so this is just what we have from here. Then we can actually do a little bit of factoring. And so you'll notice that each of the summations, we can actually factor out a 2 over 3. So now 2 over 3, then factor this out. So we have, so this will be a 1, add this with 1/2, add this with 1 over 2 squared, then add this with 1 over 2 to the power 3. Just keep going. Then we have 1 divided by 2 to the power n. What you'll notice that in the parentheses, we can actually write this as a, infinite sum, since we're taking this as it goes to infinity as well. So here we have 2 to the power 3, then multiply with the sum, the infinite sum from n is equals 0, and then all the way up to 1 divided by 2 to the power n. You'll notice that you can actually just apply the partial geometric series, or the infinite geometric series. So since, because the ratio is in between, it's less than 1, so we can use that. So it's 2 over 3 times 1 divided by 1 subtract 1/2. Then therefore that's just equal to, so this is 1 divided by 1/2. So flip the reciprocal, so therefore the final answer, so the total area is actually just equal to 4 over 3, like so. And so there we have it. In this orange box is our finite area of the continuous sequence of functions of the shaded area continuously going on to infinity. So yeah, see if you can actually evaluate this so you get the final answer of 4 over 3 without having to do all this work, this long work here. If it's impossible and this is the only method, then please let me know in the comments. So yeah, that's pretty cool if you ask me.